Hello everyone, my name is Hirotaka. I'm an orthopedic surgeon in the Sendai City Hospital, Sendai, Japan. The title of this presentation is Intramedullary nail for proximal humeral fracture should be placed within 4 mm from the bony surface of humeral head. In the present study, geometric data of intramedullary nail was provided by Japan MDM Incorporated. Two-part surgical neck fracture is one of the most common shoulder injuries, particularly in the elder population. Here, you can see the typical surgical neck fracture of the humerus. Intramedullary nail has been widely used for this fracture since it can provide secure anatomical reduction with a minimal surgical invasion. In this procedure, it has been reported that the insertion depth of the nail is one of the most important issues to obtain satisfactory clinical outcomes. If the nail position is too high, acromial impingement may occur by the tip of the nail. On the other hand, if the nail is inserted too deep, lateral screws may damage the axillary nerve. Unfortunately, however, the biomechanical laws of inserted depth of intramedullary nail has not been fully clarified yet. The purpose of the present study was to clarify the biomechanical roles of insertion depth of intramedullary nail in the treatment of two-part surgical neck fracture. Materials and methods. First, two-part surgical neck fracture model was developed. CT data of a normal shoulder were obtained from 71-year-old female. These data were imported to the software Mechanical Finder Extended Edition version 12 to develop the bone model. Then, a 1 mm thick board was imported to the model to create a gap at the surgical neck. Next, a wrist proximal humeral nail was inserted into the model to fix the fracture of surgical neck. The original insertion depth of the nail was determined as 2 mm from the bony surface of the humeral head. To create the entry hole of the nail, a cylindrical material whose diameter was exactly identical to that of the nail was placed on the upper end of the nail. In the present study, we developed 5 models that differs only the height of the upper end of the nail. First, we put a 2 mm thick disc on the top of the inserted nail of original model, which made the upper end of the nail equal to the bony surface of the humeral head. In the clinical practice, this disc is called as an end cap, which is used to adjust the height of the inserted nail. Then, the upper part of the inserted nail was resected for 2, 4, and 6 mm using the cylindrical material to create 4, 6, and 8 mm models respectively. As for the contact conditions, contact elements were inserted around the nail inside the humeral head. Friction coefficient was determined as 0 in the present study. In the boundary conditions, we attempted to simulate rehabilitation in the early postoperative period. To simulate shoulder abduction exercise, a tensile load along each calf tendon was applied on its footprint. The amount of load was determined based on our previous study. In the constrained conditions, the distal end of the humerus was completely constrained in the present analysis. Then, elastic analysis was performed to investigate the stress distribution within the humeral head. A 10 mm cubic area was set both in the proximal anchoring point and around the most proximal screw to quantify the mean equivalent stress in each area. Results. This slide shows the distribution pattern of equivalent stress inside the humeral head in 0 mm model. As you can see, a high stress concentration is seen both in the proximal anchoring point and around the insertion side of the most proximal screw. In the 2 mm model, the distribution pattern of equivalent stress is almost identical to that of the 0 mm model. In the 4 mm model, the area with the high stress concentration in the proximal anchoring point becomes narrower than that in the 0 and 2 mm models. Interestingly, a stress concentration newly appears lateral to the proximal end of the inserted nail. In the 6 mm model, the area with the high stress concentration in the proximal anchoring point almost disappears. On the other hand, a high stress concentration around the most proximal screw gradually becomes wider. A high stress concentration lateral to the inserted nail is also seen in this model. In the 8 mm model, again, you can see no stress concentration in the proximal anchoring point, a high stress concentration around the most proximal screw, as well as the lateral aspect of the proximal end of the nail. This graph shows the mean equivalent stress in the cubic area placed in the proximal anchoring point. As you can see, mean equivalent stress decreases both in the 6 and 8 mm models. On the other hand, mean equivalent stress around the most proximal screw increases with increasing the depth of proximal end of the nail. Discussion. In the present study, from 0 to 4 mm models demonstrated the highest stress concentration in the subcondylar bone in the proximal anchoring point, which plays an important role to avoid postoperative varus deformity. However, both in the 6 and 8 mm models, the size of stress concentration shifted to the cancellous bone lateral to the proximal end of the nail, as well as the cortical bone around the most proximal screw. Particularly in the case with greater tuberosity fractures, weakened bone may fail due to mechanical stress, which eventually caused varus deformity. There are several limitations in the present study. First, all the models were developed from CT data of a single patient. Second, we did only elastic analysis in the present study. Fracture prediction was not performed. Further studies including fracture prediction with large number of models would be necessary to clarify the true biomechanical role of insertion depth of intramedullary nail. In conclusions, the area of stress concentration changes with increasing the insertion depth of intramedullary nail. We believe that the proximal end of the nail would better be placed within 4 mm from the bony surface of humeral head to avoid postoperative varus deformity. Thank you very much for your kind attention.